Here's the last section in Chapter 4, which is Section 4.7 on the applications of Newton's laws. Our goals here are to accurately diagram the forces acting on an object so that we can apply Newton's laws and solve some force problems that do involve some multiple directions. We also want to be sure that we understand the conditions necessary for equilibrium, as they will determine how we will set up problems, and be able to apply those concepts to solve those problems. Some of the things that we need to go into any force problem with is an understanding of our assumptions. At this point in time, we are going to assume that we are either in an equilibrium situation or that the object is accelerating under a constant force. Constant forces, again, are going to result in those constant accelerations, and we can apply our F equals ma equation to those types of problems. We are also going to assume that there is no rotational motion that's going to be considered or addressed just yet. Basically, we're going to have these things behave as particles, so they will not be an extended object that has the ability to rotate. For now, we'll be working with frictionless surfaces, so as we address some of these problems here, we will ignore any friction that might be there. And anytime you see the words light or negligible mass, that's going to indicate that the mass is going to be ignored. Usually you'll see these on things like strings, ropes, cables, and we will ignore those masses for now. These are situations that we are basically going to be simplifying as we just begin our study of force problems. As we progress through the course, however, we'll begin to look at how to address things like a non-constant acceleration or force, how to address rotation, friction, and all those things will come up later on. We do need to understand that a tension force may be occurring in some of the problems that we'll see. Those tension forces are just any sort of a pull that's actually through a string, a rope, a cable. Now, when we're solving force problems, there are a few steps that we will want to keep in mind that will help us in solving those problems. Basically, we always want to start with drawing a free body diagram. As you're drawing your free body diagram, you want to be sure that you are identifying any and all external forces that may be acting on the object. So just as an example here, we'll look at a few forces from gravity, normal force, maybe a tension in a rope. Later on, we'll start to include friction. Those are all forces that we want to be sure that we can identify on the object. And we want to be sure that we can draw that free body diagram of those external forces. Then, once we have all those forces, we can apply them to Newton's second law. Sum up all those forces, set it equal to ma, and we would have to do that in the x or the y direction separately. Let's look at some examples. So let's say that a crate is being pulled along by a rope. We're going to look at diagramming all the forces that would be acting on this crate and take a look at what the free body diagram would look like. The rope might be attached in such a way that it could be pulling at an angle. It doesn't necessarily have to be pulling straight left or right. So if we kind of stick this on an axis here, we would have some angle theta that might exist between the rope and the positive x direction. Now as we start to examine the forces acting on this crate, of course you have the tension force in the rope itself acting at that angle theta. The box itself would also have some weight to it. So we would have an F sub g, which would just be the mass of the crate multiplied by the pull of gravity, or 9.8 meters per second squared. And of course, the surface is going to help support or hold the box up, so there's going to be a normal force. Now, the only one of these forces that isn't perfectly on one of the axes or directions that we have set up is the tension force. So tension would have to be broken down and look at how much of this tension force is in the x direction. That would basically be t cosine of theta. And how much of the tension force is in the y direction. That would be t sine of theta. Now, as we look at what this would appear to look like as we actually plugged it into Newton's second law, ultimately what we would do is we'd look at Newton's second law in both directions, in both an x and a y direction. In the x direction, we can see that the only force in the x direction is going to be the t cosine of theta. It's the only force that we have in any of the x directions, so t cosine of theta could be set equal to the mass of the crate multiplied by its acceleration. In the y direction, however, we have a lot of stuff going on. We need to consider all forces in the y direction. In the y direction, we have the normal force from the surface helping to hold the crate up. We also have the y component of our tension force in the line that is also pulling up on the crate. And finally, we have the weight of the crate pulling in a downward direction. So I have the normal force plus t sine theta minus F sub g. Now, if this crate is not accelerating up or down off of the surface at all, we could set this equal to an ma where that acceleration would be equal to 0. So in this case, we might only be solving for the acceleration in the x direction, where a would now be equal to t cosine theta divided by an m. Now, in looking at third law pairs, just to review what we talked about last time, third law pairs would essentially be the tension in the rope pulling on the crate and the crate pulling back on that rope. We'd have the third law pair from the normal force, the floor or the surface itself pushing up on the crate and the crate pushing down on the surface. And then, of course, you've got weight, where the third law pair to the earth pulling down on the crate would be that force of the crate pulling back up on the earth. To continue with our problems and examples, we want to be sure that you understand what equilibrium actually is. Again, equilibrium could be where the object is actually at rest, where it's not moving at all, or equilibrium could also be moving with a constant velocity. As long as there is no net force and no acceleration, that would be considered an equilibrium. So, in 3 dimensions, that would mean that the sum of the forces in x would be equal to 0, the sum of all the forces in the y direction is equal to 0, and the sum of all the forces in the z direction would also be equal to 0. We may need to treat some of those components or directions differently. Maybe something is in equilibrium in the y direction, for example, but in the x direction, it's under a net force. So there we would have the sum of our forces being set equal to ma. Just like in the last example, in the y direction, we had an equilibrium and could set the y direction equal to 0. In the x direction, we did in fact have an acceleration taking place, and we could solve that sum of the forces equal to ma in that particular direction. Let's take a look at another example. Here we're looking at a traffic light, where that traffic light is weighing 122 newtons. So if I draw out this traffic light here, I know that the weight of this object is 122 newtons. So my F sub g would be equal to 122. We know that this light is going to be suspended or be hanging from 2 cables, where each cable is going to make a 60-degree angle with the vertical. So this angle is 60 degrees, and this angle over here will also be 60 degrees. Now let's say that the cable itself is able to withstand a force of 100 newtons before the cable would break. So each side could have 100 newtons of force in it. We want to know, is this traffic light going to remain in equilibrium, or is this setup not going to work? In order to do this, we need to sum up all of our forces. In this case, of course, we have F sub g. We already drew that force in there. We have a tension in cable number 1, and we have a tension force in cable number 2. Each of these tension forces, we can see, can be broken down into components. Some of T1 is pulling in an upward direction, or the y direction, and some of T1 is pulling across to the right. When we look at T2, some of T2 is also pulling upwards in the positive y direction, and some of T2 is pulling to the left. These components are going to be considered when we start to sum up our forces and set them equal to ma. When we look at the forces that are in the x direction, we can see that the 2 components here are the only forces in the x direction. Basically, these are T1 sine of 60 pulling to the right, and T2 sine of 60 pulling to the left. So we're going to put a negative sign in front of that. Now this stoplight should not be accelerating to the left or to the right, so we can simply set that equal to 0, which ultimately just ends up telling us that T1 and T2 are going to be the same thing. As long as these angles are identical, that's going to be the case. Each rope is just going to support its fair share of the total weight. So let's now look at the y direction. In the y direction, pick a different color here to make this easier to see. In the y direction, we said that we had gravity pulling down, and we had these components from each of those tension forces pulling up. So we have a t cosine of theta pulling up, and another t cosine of theta pointing up. And we also have the weight of the object that is pulling down on it. So that would be a downward or negative force. So we have a minus 122. And this should be set equal to ma. But again, the idea is asking, do we actually have this thing remaining in equilibrium? If it's remaining in equilibrium, the acceleration should be 0. So we want to see what would the tension forces in each of these lines have to be in order to suspend this stoplight and actually make it stay in equilibrium. Now, because this t is the same, we just kind of proved that when we talked about the x direction, we could really just write this as a 2t cosine of 60 degrees. And we can move the 122 over to the other side. This better be equal to 122. Essentially, all of the force that we have going up better be equal to all of the force that we have going down so that the object, in fact, is in an equilibrium. When we solve this, you can pull out your calculators and try it out yourself. When you solve this, you find that T would be equal to 122 newtons. So if each cable could only withstand 100 newtons, this thing is going to break. And now we would know that we would need to choose different cable, maybe a heavier cable, that can support more weight. In fact, the wider we decide to spread these cables here in pulling on this, the higher that force is going to be. If we bring them up and make an angle less than 60 degrees, that would result in forces that would be a little bit less. So that would be another option in having these cables actually remain intact. When we come back to class, we are going to look at what happens when we take these cables and instead of having each of them at the same angle, what if they were at different angles? We'll use the same exact concepts for setting up those problems and summing up the forces in both the x and the y directions, but we'll look at the problem getting just a little bit more interesting by placing these ropes at a different angle.